Hello everyone, welcome to EEEE Lecture number 11A. Today we are going to solve some practice numericals. So there are two sets, set A and B, and the syllabus is module number 1, that is DC circuits. So let's begin. So question number 1A is asked for 10 marks, and the question reads as, in the following network, determine the voltage across 3 ohm resistance using mesh analysis. So at first sight, let me expand it a little. So at first sight, the current flowing through 3 ohm resistance, let me mark it as I3 ohms. So that these currents are already defined, I1, I2 and I3. So current flowing through 3 ohm resistance, let's consider it's flowing down. So that will be I1 minus I2. All right. So in short, we need to find I1 and I2. So let's start solving. Let me use blue color. So let's apply KVL. Let me expand it further. Let's apply KVL to loop number 1. This is my loop number 1. So let me highlight my loop number 1 with yellow color. This is loop number 1. It has been shared with, this 2 ohm is shared with loop number 3 and 1. This 3 ohm is shared with loop number 1 and 2. Alright, so let's apply KVL in loop 1 or mesh 1. So we'll be using mesh analysis. Alright, so here it is minus, this is plus, so it is rise in potential. So that will be 10 minus 1 into I1, that will be I1 minus twice I1 minus I3, and further minus 3 I1 minus I2. So if we rearrange it in terms of I1, I2, I3, you will get minus 6 I1 plus 3 I2 plus 2 I3 is equal to minus 10. Let's call this equation number 1. Now we solve, we apply KVL to the next loop, that is loop number 2. So let me highlight loop number 2 in green color. This is my loop number 2. So I'll apply it KVL over here. So KVL to loop 2. Alright. So if you see carefully, even if you apply KVL in loop number 2, there is a current source. So whenever there is a current source, your I2 will be directly equal to 5 amperes. Alright. So in a loop, if this current source is not shared by any other loop, then the value of the current will be equal to the value of the current source. So I2 is actually 5 amperes. Let me mark it equation number 2. Alright. Now let's apply KVL to loop number 3. This is my loop number 3. Alright. So let me use blue color. So let me write KVL to loop 3. Alright. So this 4 ohm resistance is set between loop 2 and 3. This 2 ohm resistance is set between loop 1 and 2, 1 and 3. So let me write down the equation. So we'll write over here minus 5 I3 minus 2 I3 minus I1, and here we'll have minus 4 I3 minus I2, and that is equal to 0. Alright, so here I will write it as twice I1 plus 4 times I2 minus 11 I3 is equal to 0. Alright, so we know the value of I2 here, so we can simplify equation number 1 and equation number 3 here. Okay, so let me rewrite this equation number 1 in green color, let's say. So the value of I2 is 5 amperes. So here we can write it as, that is minus 6 I1 plus 2 I3. This is becomes 15, and it goes on that side, it becomes minus 15. So minus 10 minus 15 is minus 25. So this becomes equation number 4. All right, let me substitute the value of I2 over here. So this will be twice I1 plus 4 into 5, that will be 20. So this will be 2 I1 minus 11 I3 is equal to minus 20. This is equation number 5. Now we'll solve equation number 4 and 5 simultaneously to find the value of I1 and I3. So let's do that. So let me write it in a matrix form. So this is I1, I2, and this will be coefficient of I1 and coefficient of I2. So minus 6 2. Here it will be 2 minus 11, and on the right hand side we have minus 25, and here we have minus 20. So solve these two equations simultaneously. You will get the value of I1 and I2. So I1 is coming out to be, let me write it as I1 is 315 divided by 62 amperes. That is equal to 5.08 amperes. And I3, I actually here it is I3. Sorry, I make a mistake over here. This will be I3. So I3 will be 85 divided by 31 amperes. So this value comes out to be 2.742 amperes. All right. So we need to determine the voltage across 3 ohm resistance. Okay. So voltage across 3 ohm resistance will be 3 ohm resistance into current across 3 ohm resistance. So we need to find the current through 3 ohm resistance. So I3 ohms will be, what was it, I1 minus I2. So I1 minus I2. So that will be I1 is 5.08. Okay, 5.08, and I2 was around 5 amperes that we got, right? I2 is 5 amperes. So this is 0.08 amperes, I of 3 ohms. All right. So what is will be the current now? What will be the voltage across 3 ohm resistance? 3 ohm into current flowing through 3 ohm resistance. So that will be 0.08. So your voltage across 3 ohm resistance is 0.24 volt, and that is the answer. So this is my answer. You can cross check it with your calculator. All right. So we have completed the numerical number 1. It should roughly take less than 10 minutes to solve this. All right. Okay. So let's go to numerical number 2. We have to find the current through 6 ohm resistance using nodal analysis. Okay. So we will be using nodal analysis over here. So first of all, we need to define the nodes. So let me use a red color. So this is my node number 1, let's say. This is node 1. Node 2, this is node number 2, 1 and 2. Let me say the voltage across the node 1 is V1 and the voltage across node 2 is V2. So this is V1 and this is V2. All right. And what we need to find? We need to find the current flowing through 6 ohm resistance. So I6. All right. Now, if we see carefully, if you have defined 1 and 2 as nodes, this is my reference node. So this becomes my ground node or my reference node. So let me solve this using red color. So over here, if we see carefully, it's a concept of super node, because a node is connected, a voltage source is connected between two nodes directly. So if you see carefully, between node 1 and 2, a voltage source is connected. So it's a problem of a super node. Okay, since node 1 and 2 form a supernode, node 1 and 2 form a supernode. So how can we relate the nodes as? This will be V1 minus V2 is equal to 12. So this is the equation we got it from the supernode concept. All right, now we'll apply KCL at supernode. So when we apply supernode at at this node over here, at the supernode, what do we get? We get the following. So we have to consider the entire node over here, like this. So this becomes my supernode. So all the currents entering, basically we can define it as follows: all the currents entering or leaving node number 1, all the currents entering or leaving node number 2. So that will be my supernode. So let's define this current as outward. Okay, this current is already inward and this current as outward. All right, so let's do that. Over here, let me define this current as let us define it as let it be. We will directly write in terms of voltages, so we'll apply KCL at supernode. So we have to apply at node number 1, but not between node number 1 and 2. All right, so this will be V1 minus 36 because we are going from positive to negative. So V1 minus 36 upon 12. Then this is outgoing current. So again it will be plus V1 upon 6. All right. And that we can write plus, here we have V1, V2 minus 6 divided by 5. So we have V2 minus 6 divided by 5, and all our outgoing currents. Now this is incoming current, and that will be equal to 2. So that is how we apply KCL at the supernode. Now we solve this further. What do we get? What is 1 upon 12? 0.0833 times V1. 36 upon 12 is 3. 1 upon 6 is 0.1667 times V1. 1 upon 5 is zero point 0.2. So that will be zero point 0.2 V2 minus 1.2. 6 upon 5 is 1.2 is equal to 12. Now if we rearrange it, you will get it as 0.25 V1 plus zero point 0.2 V2 is equal to 6.2. Let's call this equation number 2. So this is my equation number 2. Basically we are finding V1 and V2, and we got two equations relating that. So let's solve it simultaneously. So we write it in the form of matrix. Okay. So here we have V1 and V2. Here we write the coefficient of V1 and V2. So this will be 1 minus 1. This will be 0.25. This will be 0.2. And the right hand side this will be 12. And this will be 6.2. Alright. So solve this simultaneously using your calculators. And you should get the value of V1 as 172 divided by 9. And that will be equal to 19.11 volt. And V2 is coming out to be 64 by 9, and that is around 7.11 volt. Alright. Now we need to find current flowing through 6 ohm resistance. So current flowing through 6 ohm resistance will be V1 divided by 6. So that will be 19.11 divided by 6, and that is coming out to be 3.185 amperes. Okay, and the current is flowing down. So this is my value of my current flowing through 6 ohm resistance using nodal analysis. I hope the explanation is clear. Again I repeat, we have first defined node number 1 and 2, and we soon found out that it's an example of a supernode. Between node number 1 and 2, a voltage source is directly connected. Alright, and then we applied the supernode across the node number at the supernode, KCL at the supernode. So we got this current outgoing, this current outgoing, this current incoming, and this current outgoing. Alright, so here it is, question number 2, and it is asked for 10 marks. Alright, now we'll go to the next numerical number 3. Here it is also asked for 10 marks. We need to find the current through 1 ohm resistance. So this is my point A. Okay. Okay. The page is loading a little. So we need to find the current through 1 ohm resistance using Norton's theorem. All right. So my load RL, I'll mark as point A and B. Okay. So we need to first find Norton's resistance, and then we need to find the Norton's current, the short circuit current. Okay, so let's start. Let me save it. So here it is A, and here it is node B. All right. So let's start it. Let me use blue color. So first we will find the Norton's resistance, Rn. Norton's resistance, Rn. And what is the procedure to find Norton's resistance? For Norton's resistance, the procedure is remove load RL and deactivate all sources. Deactivate all sources. So what will happen to voltage source? Voltage source will become short circuit, and current source will become as open circuit. So let's draw the circuit again over here, and we need to remove load RL. So here this will become as short, 4 volt will become short. Then we have this resistor. Then we have to remove load RL. So this is point A and this is point B. Alright. So here the current source is open circuited. Here we have another resistor over here, and this current source is also open circuited. So we have 3 ohm over here, and you have 2 ohm over here. Alright. So if you see carefully, we need to find the current flowing through. We need to find the equivalent resistance between point A and B. So if you see carefully over here, RAB is nothing but 2 ohm resistance, right? So this diagram we can draw it again as 2 ohm, point A and point B. Okay, so because 3 ohm resistance here it is open circuit, so this will be redundant. 2 ohm resistance it is connected to the A and B, so we have RAB as 2 ohm. So we will mark it as 2 ohm resistance. So RAB, or we can call it as Norton's resistance, Rn is equal to 2 ohm. Alright, so we have found out the Norton's resistance. Next we need to find the Norton's current. So for the Norton's current, what is the procedure? We write over here Norton's current IN, or it is a short circuit current. So what do we do over here is we remove load RL and we short circuit A and B terminals. Okay, so let me redraw the circuit again over here and show it to you. So this is my current source of 1 ampere. Then I have 2 ohm resistance over here, 3 ohm resistance over here. This is 2 ohm, this is 3 ohm, and we short circuit this. Here we have a voltage source and here we have a current source. Alright, this is 2 ampere. This is my short circuit current IN, which we need to find out. This is 2 ohm. Let me mark the short circuit current as IN flowing down. Alright, and this voltage is 4 volt. Now we can simply apply over here the mesh analysis and find out the answer. So we'll define, and let me maximize this part. We'll define 3 currents over here because we have 3 loops. So this will be, let me define this as I1, this as I2, and this will be I3. So we need to apply KVL through I1, I2 and I3. Alright. So if you observe carefully, what is I3? We have a current source connected. Alright. So I3 directly will be 1 amperes. Okay, because we have a current source connected over there, which is not said with any other loop. Similarly, I2 will be minus 2 amperes because it is not said with any other loop. And for I1, we need to apply KVL to loop number 1. So this is my loop number 1. I need to apply KVL over here. Alright. So I'll write KVL to loop 1. So we get here it is minus plus. So there's a rise in potential. So we write 4 minus twice. This is 2 ohm resistance. Actually, sorry for written twice. So it is 4 minus 2 times I1 minus I3. I1 minus I3, and that is equal to 0 because here there is nothing. This is a short circuit and that is equal to 0. Now 4 minus twice I1 is I3 is already given, so it will be I1 minus 1 equal to 0. So from here we can find out the value of I1. So I1 is actually, here what we can do is, here we can write it as 4 minus 2I1 plus 2 is equal to 0. So we get 6 is equal to 2I1. So I1 is coming out to be 3 amperes. Alright. So we got the value of I1, I2 and I3. And now we need to find the Norton's current IN. So IN will be I1 minus I2. Why I1 minus I2? Because I1 and IN direction are same and I2 is opposite direction to IN, Norton's current. So I1 is basically 3 amperes and I2 is minus 2. So 3 minus or minus 2 and IN will be actually 5 amperes going down. So this is my Norton's current. Alright. So once we have found out the Rn and In, we have to draw the Norton's equivalent circuit. So for Norton's equivalent circuit, let's draw it over here, then this small space. So Norton's equivalent circuit says that we have a current source And parallel to that current source, we have Norton's resistance Rn. This is In. And then we have point A and B. And between point A and B, what do we have? The resistor RL. So basically, we need to find the current through the resistor IRL. Okay, or this RL is actually 1 ohm resistance. So what will be IRL? IRL we can find using current division rule, CDR. So what does it say? Other resistance. So other resistance is Rn, and how much is Rn? Rn is 2 ohms. This is 2 ohms, and IN is how much? IN is 5 amperes. Alright, so IRL will be other resistance, that will be 2 ohms divided by total resistance, that is 2 plus RL is 1 ohm into 5 amperes. So that will be 10 divided by 3. So IRL is coming out to be, let me write it over here. IRL will be 10 by 3. That will be 3.33 amperes going down. So this is my current flowing through. The load resistance is 3.33 by using Norton's theorem. Alright, in this way you can solve this numerical very easily. Alright, so that's all for lecture number 11A. Next time we'll solve another numerical, another set. So this was set number A. Next time we'll solve set number B in EEE lecture number 11B. Alright, so if you have any queries you can ask right now, or else that's it for the lecture, and thank you all for joining.